Hi there, folks. Today we're looking at isosceles and equilateral triangles. All right. So an isosceles triangle is just a triangle that has two congruent sides. All right. So when we look at an isosceles triangle, the way we refer to this is the angle that's kind of at the top of this thing we call the vertex. And I use the top loosely. Obviously, we could rotate this thing around, but really it's the one in between the two congruent sides. All right. When we refer to the other side, the one that's not one of the congruent sides, we call it the base. And a lot of times we'll think of the base almost like the bottom, so that's why I say the angle at the top. But keep in mind, if I could flip this thing over and then that angle would be on the bottom. In terms of reorienting this thing, when the base is at the bottom, the vertex is at the top. So the vertex is in between the two congruent sides. The base is kind of the bottom of this thing. It's the non-congruent side. And then when we talk about the congruent sides, we call them the legs, all right? And then in addition to that, the angles that are kind of touching the base, that are between the base and the legs, those are called the base angles. So we have all these different pieces. As I start to refer to these things, it's just a quick way to reference what I'm talking about in terms of the triangle. So when I talk about the vertex, I'm talking about the angle that's in between the two congruent sides. If I'm talking about the legs, I'm talking about the two congruent sides. Talking about the base, I'm talking about the non-congruent side. And again, we typically orient this thing so that the base is on the bottom. If I talk about the base angles, it's like the bottom angles, all right? So the two angles at the bottom, it's the angles in between the base and the legs, okay? So those are the different pieces of an isosceles triangle, so when we start to refer to those things, all right? So let's talk about the isosceles triangle theorem, all right? This is basically something that we will use a ton. We have to prove that it's true first, all right? So we're going to use this a bunch, but we have to make sure we prove that this is true first so that we're allowed to use this. And the idea here is if I have an isosceles triangle, and that's based on what's given here, AC being congruent to BC, all right, I want to prove that the base angles are congruent, that angle A is congruent to angle B. Those are the base angles of this isosceles triangle. I want to prove that when I have an isosceles triangle that those base angles are the same, all right? And after we prove this, this will be part of our toolkit again, all right? So if I look at something like this guy, I'm going to list my statements and reasons here. Prove those base angles are the same. And so I start with what I'm given. Let me mark it over here that these are congruent, okay? So AC is congruent to BC. And again, that's given. From here, if I have a triangle where two of the sides are the same, I can say that this thing is an isosceles triangle. That's not really going to help us get through this proof in any way. What it will do is it'll help us talk about the different pieces, but it'll also help us say at the end that, this was an isosceles triangle. You could include that here. It doesn't really benefit us in any way. Again, it's part of the idea that I'm trying to prove something about isosceles triangle. All right, we don't need to state that here. All right, so if you're thinking, oh, I have an isosceles triangle, that really doesn't help us. Later, that'll help us once we have this theorem in our pocket. So going from here, I got nothing. Yeah, I could say it's an isosceles triangle, but that doesn't really do much here. The problem is that I just don't have anything else to go off of. Here's what I have to do, all right? I have to draw something else. And this has happened before. When we kind of run out of stuff and I don't know what to do, I have to add something to this picture. And keep in mind that I can construct certain things on this picture, all right, that will benefit me, all right? So here's what I'm going to do. I'm going to draw a line that goes right down through the center of this thing, right here, okay? And see, I can do a couple different things with this line. I could say that it's an angle bisector, and it bisects angle ACB, all right? That's something I'm allowed to say because I could construct it that way. I could draw a line that purposefully cuts that vertex angle in half, all right? I could also say that, I'm going to draw from C to the midpoint of AB, so I could label this point right down here as something like D and say, you know what? I'm going to say that D is the midpoint, all right? So not talking about the thing being an angle bisector, but say, hey, I'm going to draw that to the midpoint. That would also be an acceptable thing that I could draw. I could find the midpoint of AB, and I could draw a line that connects C to D, all right? And so there's a bunch of different options here. we could use any one of them. Any one of these is going to be fine for our purposes. Why don't we go with the idea of D being the midpoint? All right. So I'm going to say what I did here. So I drew CD. Oh, sorry. That's going to be my justification. I'm going to say that D is the midpoint of AB. Okay? And the idea here is that it's that way because I drew it that way, because I said so, all right? I'm allowed to create that. That is something that I can create, so I'm going to say that's what I created, okay? And anytime I do that, I say I constructed CD, so D is the midpoint of AB. Okay? And it's as simple as that. When I draw something on here, as long as it's something I am able to construct, I am allowed to list that on here. Okay? So I constructed that so that it would be so. All right? And so now from here, I can use that information. I can say, okay, well, if D is now the midpoint, I could say that AD is congruent to DB. And that's because that's what a midpoint is, all right? That's my definition of the midpoint. And then step 4, sorry, let me label that on the graph, these guys. And so right now I have two sides, those little triangles on each side. And so hopefully you're looking at this thinking, hey, we've done a proof almost just like this before. I have these two triangles. Maybe I should keep going and see if I can prove that the two triangles are congruent that I've made here, those little two triangles. And the idea here is if I had two of the sides, so can I get side, 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 or side, angle, side out of this thing? Well, side, side, side's really easy because the third side, the side that I'm missing, is CD for both triangles. So I'm going to say that CD is congruent to itself. And again, that's my reflexive property. I can label that up here. This guy is congruent to itself. And now because I have side, 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 all three sides from one triangle congruent to all three sides from the other triangle, I can say that the two triangles are congruent. So triangle ACD was one triangle. Triangle BCD is the other triangle. And that was because of side, side, side. And keep in mind that angle A and angle B are pieces of the two triangles that I'm talking about. See, when I look at A and B, this is just me proving that the pieces of two triangles that are congruent. So I can say that angle A is congruent to angle B. And that's because of CP, Okay, corresponding parts of congruent triangles are congruent. See, I'm using the same things that I've been using, but I'm using it in a unique context now. And so what this is showing me is I started with an isosceles triangle, and I ended up showing that the base angles of that triangle, that this angle and this angle are congruent. All right? This is the isosceles triangle theorem. Okay? Isosceles triangle theorem, if two sides of a triangle are congruent, then the angles opposite those sides are congruent. And essentially, if you want to just state it when you go to state this thing as, hey, the base angles of an isosceles triangle are congruent, that would be an acceptable way to state this. Okay, but that's what it's saying. All right, the base angles are the ones that are opposites those sides. They're between the base and the congruent sides. The converse of this is also true. So basically, if I have two angles, two base angles that are congruent, I can immediately say that this thing is an isosceles triangle, that those opposite sides are congruent. Okay, so this theorem works both ways. All right, and we could prove it the other way as well. The proof would be very similar. All right, but we're not going to waste our time to do that. We're just going to say, okay, we proved this thing. The converse is also true. So if I have an isosceles triangle, the base angles are congruent. If I have base angles congruent, then I know it's an isosceles triangle. Okay? Oh, and the other thing, just to run back to this thing, if I had drawn that line CD so that it was an angle bisector, so that I had the two top angles congruent, I would have gone through the same thing, but it would have been side angle side that I used to prove the triangle's congruent. Okay? The only difference would be the step where I mentioned the midpoint. I would have said the angles are congruent because of the definition of an angle bisector, and then my justification for the triangles would have been slightly different. Okay? So keep in mind, there's multiple ways to do these proofs, and as we get further and further into geometry, there are more and more options for how we can approach the different proofs that we have. Okay? There becomes more than one path to get to that proof statement. If I look at this next one, so kind of bringing this back to some algebra-based type of stuff, here I have an isosceles triangle, and I know it's isosceles because two of the sides are congruent. It's listed that way. So if I have an isosceles triangle, I know the base angles are congruent, which means this angle right here must also be a 2x minus 5. Okay? And then the idea is, well, if these are three angles inside a triangle, I know that they add up to 180 degrees. So to solve this, I can say that this guy plus this guy plus this guy equals 180 degrees. And now I can use that to solve for x. So here I combine like terms. That's going to give me a 5x minus 10 equals 180. Let me bring that work up here. I add that 10 to each side, and then I divide by the 5. My brain is having a little trouble. There we go, 38. And here's the thing. This one, I'm just going to find the value of x. If I wanted to, I could easily find each angle now, okay? If I look at the next one, same kind of thing. It's an isosceles triangle because it's listed that way, it's shown that way, it's drawn that way because of those two dashes. So now I know the base angles are congruent, so this has got to be an x, okay? And then from there, I can say, hey, the three angles inside this thing, once again, add up to 180 degrees. So that's a 2x plus 15 equals the 180. Once again, let me drag this guy up here somewhere. So I subtract that 15 from each side. That's a 165. And then I divide each side. That's an 82.5. Okay? And so once again, I'm just finding the value of x. If I want to, I can easily go back and find the measurements of each of those angles. Okay? How about this one? It says, name all the congruent segments. All right? And notice I'm starting with an isosceles triangle down at that bottom corner. That ABC is an isosceles triangle. But then it also tells me that angle A and angle E are congruent. Okay? And so there's a couple different things that happen here. One, I know right away that AB and BC are congruent because, well, it's listed that way. So I should start with that. Okay? But then the other thing that I know here is I know that the entire big triangle is also an isosceles triangle. And I know that because the converse of the theorem we're talking about here, the base angles are congruent, which means the big triangle is an isosceles triangle. So therefore, AD is congruent to DE, or ED. Doesn't matter how you list it. Okay? From here, students might look at this and say, well, it looks like AB is congruent to BD, all right? But again, it's not about what looks congruent, it's about what we can prove to be congruent. And so this one, I can't prove that those are congruent, all right? I'm not able to do it, so that's kind of where I have to stop, all right? It also says to name all congruent angles. Well, right away, I know that angle A is congruent to angle E because it's listed that way, it was drawn that way, it was shown that way. But then also, because I know that that smaller triangle is an isosceles triangle, I know the triangle ABC is isosceles, I know that the base angles are congruent, so these guys are congruent as well, A and C, okay? And there's actually one more thing that I can say here, and it's kind of that idea of the transitive property. If E was congruent to A and A is congruent to C, then C is congruent to E as well. And now that I've marked that on the picture, you can kind of see it that way as well. All right. So don't forget about that relationship. There's one more kind of added in there. All right. We have one more theorem here. If a line bisects the vertex angle of an isosceles triangle, then the line is also a perpendicular bisector of the base. And this is one we're not going to go through the actual proof. It's not a very difficult proof. It's very similar to what we did before. And when you kind of start to think about this, well, of course that's going to be true. Because as you kind of look at the proof we did before, we used two triangles when we cut this thing down the middle. So when we cut that isosceles triangle in half, let me draw a picture of it. So here I had an isosceles triangle, right? And when I cut it down the middle, part of that proof was showing that these two smaller triangles are congruent. And if you start thinking about all their different pieces, like this guy congruent to this guy and these guys congruent, think about the angles. This one's congruent to this one. These guys are congruent to each other. But then these guys right here, and these are the ones we want to focus on, these angles are congruent. And so here's the thing. If those angles are congruent, sorry, I erased a little bit too much. If those bottom angles right there are congruent, this set right here, this guy and this guy, they have to be right angles. And you see, they have to be right angles because that is a linear pair. And that's kind of how this proof would go. It's the same as the proofs we've been doing. We'd show that those two triangles are congruent. Then we'd say, wait a minute. If those angles are congruent and they form a linear pair, they each have to be 90 degrees. Okay? That's kind of the way the proof for this theorem would go. We're not going to go through it, so just talking about it a little bit. But then also, we can see that that is a perpendicular, so we can see that it's perpendicular, but it's also a bisector. Let's look right here. We have these two pieces congruent. So it is a perpendicular bisector, and we can show that just using CPCTC over and over again with those two smaller triangles. So it's very similar to the proof we already did, all right? But kind of think about where that comes from, all right? So again, the idea here is, isosceles triangles are really special in that way that if I drop that perpendicular line or an angle bisector down the middle, it's not just an angle bisector, it's also a perpendicular bisector, okay? And kind of gives us these two right triangles. For example, if I look at something like this guy, again, when I drop that thing down, I know those two triangles are congruent, which means that, hey, this is a right angle, this is a right angle, these guys are congruent to each other, all right? And that's kind of what this theorem is saying. It's saying, hey, we know from the proof that we did that if I drop that line down through, that I end up with two congruent triangles. Well, that's just what happens every time. So if these guys are congruent, it means that this thing going down through here is a perpendicular bisector, okay? And so what I can say is that y is the same thing as this guy over here, so this is also the equivalent of y. I know that the base angles are congruent, so I can jump over here and say, hey, this is a 54 degrees, all right? But then the idea, I know that this is 90 degrees, that allows me to find x. See, right here, the angles inside this triangle add up to 180 degrees. So let's see, it's 54 plus 90 plus x has to equal 180, okay? And so that's the idea here, is that we can kind of use this and create these right triangles based on the information I have. So when I add these together, let's see, 144. And I subtract that 144 from each side, so it looks like a 36 degrees, okay? So there's x. Let's talk about the y values and the z value here. If I have this guy down here as being 10, well, since this thing gets cut in half, that bottom segment, that base of this thing is being cut in half because, again, that's a perpendicular bisector. Well, I know that y is 5. And here's the thing. You don't have to go crazy showing me that, oh, it's got to be y plus y equals 10. All right, we know that those are the same. That's going to be 5 centimeters, okay? And then the last one here, z, is probably the one that students find the trickiest. It's the idea that this is a right triangle. We want to use our Pythagorean theorem. See, it's going to be z squared plus 5 squared equals 15 squared, okay? And so when you look at that triangle kind of separated out from the rest, it's a right triangle where z is here, this is 15, and this is 5. It's simply my Pythagorean theorem. Bring it down here. Z squared equals 200. and then I take the square root. And if we're leaving this in exact terms, that would be 10 root 2. And again, that's centimeters. All right? It really depends on the question. If it asks for the exact answer, this is how you would leave it when you take the square root of each side. If it asked for this thing as a decimal, well, then you plug it into your calculator. All right, let's talk about equilateral triangles. Equilateral triangles are triangles that where all three sides are congruent. And so here's the thing. If all three sides are congruent, that means we still have two congruent sides. So all the same rules for the isosceles triangle, we can apply to an equilateral triangle. All right? So keep that in mind. You could still drop an angle bisector, and it would be a perpendicular bisector. Okay? If you viewed the equilateral triangle as an isosceles triangle from a certain perspective, you would see the base angles are congruent. Okay? But then if you turned it, the base angles would still be congruent. And if you turned it again, the base angles would still be congruent. So as you kind of think about this thing, and you'll see this in a moment, if these base angles are congruent, we'll now turn it so that these angles are now here. Well, now the base angles are congruent. And so we start to realize, okay, well, now all the angles are congruent. Okay? And so let's talk about a corollary. So a corollary is a theorem easily proven by another theorem. And so the corollary to the isosceles triangle theorem, if a triangle is equilateral, then it's equiangular, which means all the angles are congruent. And that's what I just did right up here, okay? This was essentially a corollary. I used the idea that, hey, the base angles of an isosceles triangle are congruent. I can view an equilateral triangle as an isosceles triangle, and so as I rotate it, the base angles continue to be congruent, which makes all the angles congruent, okay? That's a corollary. I used an isosceles triangle theorem to easily prove that all the angles inside of an equilateral triangle are congruent, okay? So that's where this guy comes from. It's what I did right here, okay? That's the idea behind a corollary. It's thinking about this thing from the perspective of another theorem, okay? So then also the corollary to the converse of the isosceles triangle, if I have a triangle that's equiangular, well, then it's got to be equilateral. So it's that idea that, I had the same thing before with isosceles. If the base angles are congruent, it's isosceles. I could do it each way, okay? If it's isosceles, the base angles are congruent. If the base angles are congruent, it's isosceles. With equilateral, it's the same thing but expanded. All the angles are congruent. So therefore, if all the angles are congruent, I can say it's equilateral. I can go back and forth, okay? And so the example here, if I look at something like this guy, I want to find the measurement of x, y, and z. This first one only has x in it. But if this is equilateral, then all the angles are the same, which means when I add them together, it equals 180 degrees. So each angle, well, each angle has to be 60 degrees, okay? And when you think about it, it doesn't matter what equilateral triangle I have, all the angles are always going to be 60 degrees because of that theorem we just talked about, or the corollary we just talked about, okay? If I look at this guy, all the angles are the same, which means this has to be an equilateral triangle, okay? Which means if one side is 5, then guess what? All the sides are 5, okay? So it's the same kind of special stuff that happened with an isosceles triangle, but even more so, because now all the sides are the same, all the angles are the same, okay? If I look at this guy, same kind of thing. I have to expand out a little bit. If I look at this from the perspective of an isosceles triangle, so we see which two sides are congruent, these sides are congruent, which means the base angles, this angle and this angle, have to be the same. And since one of them already has one arc, this one would also get one arc. And so what happens immediately is I see now that all the angles are the same, which means this is an equilateral triangle. All the sides have to be the same, okay? But it's that transition of, okay, how do I know this is an equilateral triangle? Because I had to think about it as an isosceles triangle first. So now I know that y equals 7 feet. And if I've been paying attention, I know that x equals 60 degrees. Without having to really do any work, this is the same example we just did. All three angles add up to 180 degrees, okay? If I look at something like this guy, I see all the angles are the same, which means all the sides are the same. It's got to be an equilateral triangle, so these guys are congruent. And it's congruent, let me do 2 dashes, to this entire bottom piece, okay? But then it's showing me that this thing, line coming down splits that bottom in half, splits the base in half. So that's a midpoint down there. So again, as I kind of work my way around this thing, this is 6. This whole thing down here is also 6. But just like with the isosceles triangle, if I break that thing in half, that means y is 3 feet. Okay? Because again, an equilateral triangle is still an isosceles triangle. It's just kind of a special isosceles triangle. If you think about the perspective of x now, well, think about isosceles triangles. If I dropped that perpendicular bisector, if I dropped a bisector down through there, it splits that top angle, that vertex angle in half, which means instead of x being 60 degrees the whole way across, x is 30 degrees now. It's that same thing that applied to isosceles triangles, but we're applying it to an equilateral triangle, okay? And then z, we can take the same approach. If I just look at a piece of this thing, we know that this is a right angle. It was 3, 6, and our good buddy z over here. Well, that's our Pythagorean theorem once again. Z squared plus 3 squared equals 6 squared, okay? I subtract the 9 from each side and get the 27. Oh, and maybe I should show this, that I took the square root of each side. That's how I did the other one, okay? And again, in exact form, that's going to be 3 root 3, okay? So again, isosceles triangles, 2 of the sides are the same. The special thing about those is if I have isosceles triangle, the base angles are congruent, okay? Likewise, if I have base angles congruent, the opposite sides are congruent. I have an isosceles triangle. Equilateral, all the sides are the same, and so along the same lines as the isosceles triangle, all the angles are the same, okay? And then I can apply the same rules to isosceles triangles as I do to equilateral triangles, and that includes the other special one that is if I drop an angle bisector, it's also a perpendicular bisector. Likewise, the reverse is true. If I have a perpendicular bisector, it's also an angle bisector, okay?